So in this video we're going to develop the solution process for when the characteristic polynomial has a repeated root. So in video 1 we looked at the first order homogeneous linear differential equation with constant coefficients. We guessed that y equals e to the rx is the solution. We discovered that if it is the solution, then the characteristic polynomial ar squared plus br plus c has to equal 0. And because we know that we can completely factor any second degree polynomial, we know that the roots r will always exist. So we're going to look in this case, or in this video, we're going to look at the specific case where we get a repeated root where r sub 1 equals r sub 2, and where those repeated roots are of course going to be real numbers. And when you're calculating, when you're trying to find the roots of this equation, one way to do it is to use the quadratic formula. So we'd get that our roots are equal to the opposite of b plus or minus the square root of b squared minus 4ac, and everything here is going to be over 2a. And what we want to remember is that when we get a repeated root, we need plus or minus nothing over here. We need plus or minus 0. So the only way that we get a 0 over here is when the discriminant b squared minus 4ac equals 0. So if we have a repeated root, we know the discriminant is 0. We know that from the quadratic formula we get negative b over twice a plus or minus 0, which is why there's only one root. When we did the plus or minus part, we only got a 0. So this was twice a. So our root 1 is going to look like the opposite of b over 2 times a. And if I multiply both sides by 2, I see that twice root 1 is going to be equal to the opposite of b over a. And this is going to be important because what we're going to use is the reduction of order technique from the previous homework assignment, which said, hey, if you have a second degree linear homogeneous differential equation in the form where the leading coefficient on y double prime is a 1, then if you know a solution, if you have a known solution, you can construct a second solution from the known. This is a formula we developed in the previous homework. We can construct a second solution from the known solution doing this by multiplying the known solution times the antiderivative of e to the antiderivative of p of x dx divided by the y sub 1 squared. And so we want to go ahead and use this formula from the previous assignment in order to construct a second solution from our known solution. We know that y sub 1 equals e to the r sub 1x is a solution to the differential equation. So we've got to first get it into the correct form. So you start with the ar squared plus br plus c equal to 0, and then we divide through by the a to get that leading coefficient. Sorry, I'm jumping ahead of myself. We start with our differential equation. That's what happens when you start thinking about other things while you're writing. You don't write what you need to write. So I need to get this differential equation into the appropriate form. So I have to divide through by a to get that leading coefficient of 1, because our solution, our formula derivation relied on that leading coefficient being a 1. And then once we do that, we have our p of x right here. Our p of x is going to be the b over a. So we just pop stuff into the formula. We say, hey, y sub 2, our second solution, is going to look like y sub 1. But y sub 1 is just this, e to the r sub 1x. And then we're times the antiderivative of e to the opposite. And then in here is going to go the b over a. But b over a is a constant, and we can factor it out. So I can go negative b over a times the antiderivative with respect to dx. And then we're going to be divided by our known solution squared. So when we square e to the r sub 1x, when we square it, we're going to get e to the 2r sub 1x, because when we square, we multiply the exponents. So we wind up with the e to the 2r sub 1 e to the 2r sub 1 x down here, and this is all dx. And when we integrate this, when you integrate dx, or 1 dx, you just get an x. So we wind up getting negative b over a times x. But negative b over a from our work here is just twice r sub 1. So I can substitute the negative b over a with twice r sub 1. And when I do that, I get e to the twice r sub 1x divided by e to the twice r sub 1x is just 1. So we're just taking the antiderivative of 1 dx, which is just x. So we wind up getting e to the r sub 1x times x, or just the order of multiplication doesn't matter, x e to the r sub 1x. And now we have two solutions, two linearly independent solutions. We have y sub 1 equals r sub 1x. We have y sub 2 equals x e to the r sub 1x as a second solution using our reduction of order work from the previous homework assignment. So our general solution, remember, is just to put your two linearly independent solutions together with constants. So we get c sub 1e to the r sub 1x plus c sub 2 times our second solution is x e to the r sub 1x. So this is the general solution always when we get a repeated root.